Okay. Okay, so I think we can start our seminar now, and our speaker is a professor of the Mathematical School of Peking University, Huijun Fan. Thank you for this talk. So you can start.
So thank you very much for the introduction from Professor Ziganov, and also thank Rashid Kikin for the invitation to the BIMSA seminar. So today I will talk about the geometry of Landau-Ginzburg model. So the reason why I chose this topic is in recent years, this model has become a popular topic in the study of Miller symmetry. But as you know, LG model actually was used by physicists to compute the quantum invariance in the 18th of last century. So today my talk consists of the following 6 parts. So firstly, I will recall some basic knowledge about singularity theory, and then I will let you see why the singularity theory appeared in the study of Miller symmetry, and then it leads to a general definition of Landau-Ginzburg model containing the part of singularity theory. And then I will tell you about the geometry related to LG models. So finally, I give some problems to our audience. Actually, the singularity theory can be considered from 2 points of view. We can consider the real case. For example, let f be a C2 function on Rn. 0 is a critical point of f. If all the partial derivatives of f at 0 vanishes, and then 0 is called then 0 is a critical point. 0 is called a non-degenerate critical point of f if and only if the Hessian matrix is non-degenerate at 0. Then after coordinate transformation, we can express f in standard form. So at the non-degenerate critical point, fx has the following expression: f0 minus quadratic terms, and the number of minus term is called the Morse index of f at 0. Given us smooth manifold M and the C2 function f, if all critical points of f is non-degenerate, then f is called the Morse function on M. The set of Morse function on M is open and dense in C2 topology. And then people try to consider the analytic properties of f with the topology of M. For example, consider the change of the level set. So the homotopy type changes if the level set cross the critical points, and this led to the study led to the Morse theory. So Morse theory is very important in the field of geometry. For example, we have many applications. We can study Morse complex, Witten complex, and then use the technicals from Morse theory to get both periodical theorem and solve the Poincare conjecture for in higher dimensions. So this is a real case. And then let's turn to the complex case. let f be a holomorphic function on Cn. Similarly, we have the definition of most critical points and the holomorphic most function. Assume that 0 is the most critical point, then locally, we also have the standard form. Fc equals to Fp plus the quadratic terms. But the holomorphic most function has a very special property. That is, if f is a holomorphic most function, and if and only if the real part of f and the imaginary of f are most functions, and each of the critical points has most index n. So n is the middle dimension, is a real middle dimension. For example, we can look at the very simple example, fz equals to z square. So this is equals to x squared minus y squared plus I times 2xy. And so you can see the real part of this function has most index 1 at 0. So for small positive numbers, delta and epsilon, we can consider the small neighborhood x of 0 in Cn. So we have this small neighborhood x, and then we can take a disk d data with radius delta in C, and then we get a vibration because the map f from x to the small disk d data provides a vibration with fiber xt equals to f inverse of t. So in this vibration, x0 is a singular fiber. For t not equals to 0, xt is a smooth fiber, which is homotopic to a sphere as to n-1, which is called a vanishing cycle. Well, we can fix a point t0 in the small disk d data minus 0. We have the relative homology Hn of x relative to the fiber xt0 with a coefficient z consisting. So this relative homology consisting of only one generator called the Lefschetz simples. For example, we can take a parameter t greater than 0. Consider the vanishing cycle st in the fiber f inverse of t. So the vanishing cycle has the following expression. So this is n-1 sphere, and then we combine the vanishing cycle together to get the Lefschetz simple. So you can see if you let t goes to 0, the sphere will become small and smaller, and then vanish as a critical fiber. So we have two local systems with fiber Hn-1 of xt and the relative homology Hn over the punctured disk. Because the local these are local systems, it's equivalent to say this fiber bundle has flat connection, and then we can. This flat connection is called the Gauss-Malin connection with respect to this local system. And then we can study the parallel transportation along the circle, along the closed loop of surrounding 0. And then we get the monodromy. So you can compare the difference between most theory and the in real case and in complex case. So in real case, you have only one. You have only one direction. You can see the level set, right? So you have only one direction. But in complex case, you have two directions. You can see the change if you let the the values of f go along the region. So this induces the complex Morse theory, the so-called Becker-Lefschitz theory. So let us consider more complete cases. If fz equals to z cubic, so z equals to 0 is an isolated critical point of f, but not Morse type. But we still have the fibration f from x. X is a small neighborhood of 0 in C3 in C goes to d delta, but more degenerate fiber x0. So in general, we assume that f from Cn0 to C0 has an isolated singularity at 0. Milner's theory says that the fiber xt t not equals to 0 is smooth and is homotopical to the one-point union of mu f spheres as to n-1, and the relative homology is freely generated by mu f generators. And so the spheres in the absolute homology of the fiber is called vanishing cycles, and the elements in this relative homology is called Lefschitz simples. Mu f here is called the Milnor number of this singularity. So Milnor number can be obtained in another way. You can consider a generic small perturbation of f, and then mu f is a number of critical points of Morse perturbation. We can also get mu f from the consideration of algebraic computation, because we can consider the Milnor ring. So we take the coordinate ring modular the Jacobi idea of f, and then we get a finite dimension C space. So mu f is a dimension of this Milnor ring. For example, we can consider the AR-1 singularity. So the Milnor ring is generated by R-1 generators, and the Milnor number is R-1. So this is a simple example. And now comes a very important problem, classification of all singularity, all local singularities in terms of the topological invariance, including Milnor number, vanishing cycles, and also monodromy metrics. So this has been studied for a very long time. So for example, the audience can see the Arnold, Guzan-Zad, and Washenko's books on singularity theory. So an important ingredient in this singularity theory is universal deformation. So we can consider capital F of ZT equals to Fz plus the sum Ti times Gi. So where Gi are elements in the Milnor ring, and T is a deformation vector consisting of the entries from T1 to T mu. For example, for the AR-1 singularity, we have the universal deformation Ftz, so equals to Z to the power of R plus T R-1 times Z to R-2 plus dots to plus the T1. So this is a universal deformation of Fz. The other deformation can be, in some sense, can be embedded to this universal deformation. And then we can consider more complicated examples appearing in the study of mirror symmetry. We can consider the so-called quasi-homogeneous polynomial W. So quasi-homogeneity of W means W satisfy this equality. So you're just inserting lambda to qi times ci into the entries of W, you get this equality. So qi here is called the charge or weight of the variable zi. And we have an important invariant, CW. CW is defined as the sum of I, 1 minus 2qi. So CW is called the charge of W. We define, so W is called a non-degenerate quasi-homogeneous polynomial if first, W contains no monomial of the form Zi times Zj for I not equal to j. And the second, 0 is a unique critical point of W. So this is a definition of a non-degenerate quasi-homogeneous polynomial. Here, I want to remind you, non-degenerate here has different meaning to the definition of Morse function. And then for this general singularity, non-degenerate quasi-homogeneous singularity W, we can calculate the Milnor number. So here, there is a formula for the calculation. So mu of W equals to the products of those numbers, 1 over Qi minus 1. And the central charge of W is just the sum of 1 minus 2 Qi. So this provides the computation of invariance of W. So besides that, W has its symmetry. So you can take you can take a diagonal matrix J. So the entries along the diagonal are the numbers e to I 2 pi Qi. So Qi are weights of variables Zi. So then the subgroup, this is a cyclic group generated by J, is a diagonal symmetry group. That means if you change the variable under this matrix multiplication, the polynomial is invariant. A diagonal symmetry group, capital G, is called admissible if the cyclic group J is a normal subgroup of capital G, and G is also a normal subgroup of the maximum symmetry group. So here is a table of some important singularities. The singularity for CW less or equal than 1 has also already been classified. For example, CW less than 1 singularity consists of ADE singularity, AN, BN, E6, E7, and E8. You see, for example, you see E7 and DN has a mixed product term. And we also have the CW equals to 1 simple elliptic singularities. The interesting case is you can see the P8. So P8 is the sum of the cubic monomials. So it can be used to define the elliptic curves in the projective space P2. And we also have Arnold's 14 exceptional singularities. Those singularities has a central charge slightly larger than 1. So this gives you a direct impression of the singularities. And then we turn to the topic of mirror symmetry. We consider a degree n plus 1 homogeneous polynomial with n plus 1 variables, W. So W is written as the following forms. So it's a homogeneous polynomial. And then you calculate the charge of charge Qi is just 1 over n plus 1. And the central charge CW is n minus 3. It's an integer. So if this central charge is integer, this singularity is called of Calabi Yau time. And we also have the symmetry group. The maximum diagonal symmetry group G max is just this product of a cyclical group. And the J group is isomorphic to this cyclical group. And we also have capital G. So this is Zn plus 1. So across n times. So this group just preserves the holomorphic volume dz1 verge to up to dzn plus 2. And then we have the Calabi Yau hypersurfaces xw, because we can take the zero locus of W. So the zero locus of W defines a smooth hypersurface inside of the projective space CPN, because W is non-degenerate, which means 0 is the only critical point of W. So this is equivalent to say this hypersurface is smooth. And we have another Calabi Yau orbifold, X check W. This is a quotient. Geometric object. You can take XW quotient G tilde. So where G tilde is a quotient group G modular the small group J. So this is just this cyclic group. And then the mirror symmetry says the topological field theory defined on XW should be equivalent to the topological field theory defined on X check of W. The most famous example is n equals to 4 case. So this gives quintuple Calabi Yau threefolds. The first observation was observed by the two physicists, Green and Placer, in the early of 80s. So they observed the following symmetry between Hodge numbers. They found H21 of XW equals to 101, but this is just H11 of X check. So here I just cheated you a little bit because here we should use the crescent resolution of X check, but of course it's equal to the Hodge number defined on this orbifold Calabi Yau manifolds. And then many physicists has found a lot of examples having such symmetries. But of course, this is not so astonishing if just only this phenomenon appearing. And then some physicists found more surprising facts. So they found this correspondence. If you want to count in the rational curves on Calabi Yau hypersurface XW, and this is equivalent to solve fourth order Picard-Fuchs equation on another side given by X check. So this is very surprising fact observed by the physicists, because counting rational curves on curved complex manifolds is a very old problem since Riemann's time. It's so at first glance it's nonlinear. It's very nonlinear things. Yeah, if you want to counting the number of rational curves, but this is transformed to the solvation of ordinary differential equations. So this was a very surprising phenomenon. So this was the start of research of mirror symmetry. Here are some very rough explanation of the mirror symmetry. So here I have to say the real reason for the symmetry has not been explained precisely. So the one explanation from physicists says this is due to n equals to 2 super conformal field theory. So this conformal field theory can be traced to two different but equivalent topological field theory called A theory and B theory on to mirror Calabi Yau manifold X and X check. So if you believe the world is unique and real, and then the observables, even they are expressed in different on different geometrical objects, they should be the same, right? So here I say just explain the so-called topological field theory means considering the quantum effects near the vacuum states. One n equals to 2 superconformal field theory is given by the n equals to 2 supersymmetrical nonlinear signal model. Its A theory is a quantization theory of symplectic structure, and its B theory is a quantization theory of the complex structure. And we can describe the mirror symmetry in a more mathematical way. So let X and X check be Calabi Yau mirror pair, then the A or B topological field theory of X are equivalent to the B or A topological field theory of X check. Of course, you can consider the closed version of topological field theory. So this conjecture and leads to the conjecture of enumeric mirror symmetry. So you calculate the enumeric, for example, Gromov-Witten invariance, and then compare them to the invariance from the B side. And you can also consider the open string theory. That means you consider the problem with boundary conditions. So nowadays, we know this is related to the category, the equivalence of category theories. Of course, between the closed and between the open and closed string theory, there should be the open to closed correspondence phenomenon. But here we don't want to mention too much along that direction. So let's see more details about the A theory. So generally speaking, A theory in mathematics means people need to solve some nonlinear equations. For example, we can consider the Calabi Yau nonlinear signal model. So let X omega J be a symplectic manifold with a compatible pair. A theory is related to the modular problem of the pseudo-holomorphic curves U from a Riemann surface sigma with complex structure J to X, which satisfy this Cauchy-Riemann equation. This Cauchy-Riemann equation is not linear if X is a curved manifold, because in local coordinates, this equation has a following expression. Yeah, so you see J is almost a complex structure on X, and J should composite of U. Yeah, so it's non-constant. So this is a nonlinear Cauchy-Riemann equation. So while very difficult technicals, people can build the quantization theory, the so-called Gromov-Witten theory, based on the modular space of curves M bar GK, and define the GW invariance. So this is a very rough description of the A theory for the nonlinear signal model. So from the B side, in some sense, this is solving some linear equation. But of course, the first step to study the B theory is to study the deformation theory of complex structures. For example, we consider X complex manifold and let Tx be a holomorphic tangent bundle. Then its local deformation of complex structure is given by the Moré-Gardin equation. So this is also a mild nonlinear equation. So we have the Pasch-Bar phi plus the Lie brackets of phi and phi equals to 0, and then we try to solve this equation near 1 point. So phi t is 0, 1 forms with the value in the gem of smooth gem of TTM. So we have two famous examples to show this. So this actually forms a DGLA, differential graded Lie algebra. So we solve this equation. We have two famous examples. Says this equation can be solved without obstruction at any point. So the first one is for the Riemann surface with genus G greater than 1. No obstruction, because the nonlinear term disappears. You only need to solve this linear equation. So this the solution of the linear equation is isomorphic to this space, this shift cohomology, and by serial duality, this is also is equivalent to the quadratical holomorphic forms, the space of this one. And then you use Riemann-Roch theory, because Km is a positive line boundary. You have the Huijun theorem, and then use the Riemann-Roch theory. You can compute the dimension of this deformation space. This is just 3G minus 3. So this is a first example. Then another very famous example is consider the deformation of compact Calabi Yau manifolds. So we have the famous 10 Todorov lemma. The Morel-Gardin equation is solvable, and the tangent space of the deformation space is given by this shift cohomology, and this is just the topological cohomology with this degree, and then near one complex manifold. Once you solve this Morel-Gardin equation, so you get a family of complex manifolds. So, for example, the XT, this is a family of holomorphic family of complex manifolds. So each fiber XT represents a manifold with different complex structure. So furthermore, if one fiber is equipped with a Kähler matrix, then by one of Kodara's theory, the nearby fiber has also a Kähler structure, which depends smoothly on the deformation parameter. And then we consider the variation of Hodge structures on the deformation space. So firstly, we consider one Kähler manifold. Let X be a Kähler manifold with Kähler form, omega. And then we study the Kähler geometry of X. So we can, that means we study the following differential operators. So there are some operators defined on X. So the first three are the so-called Lefschetz operators, L, lambda, and F. So L means you can merge with a Kähler form, and the lambda means you can take contraction with a Kähler form. So F is the number operator. The three operators forms a SL2C algebra. And then you consider, because it's a complex manifold, you can consider the D bar operates, D operates, and the real exterior differential, so which is equals to D bar plus D. And because you have the metric, you can use them to define the dual operators D bar star and D star and D star. You can get the Laplacians, the real Laplacian, and also the complex Laplacian defined by the D bar operators. Because X is Kähler, it turns out the complex Laplacian is just half of the real Laplacian. And also by the Kähler identity, we can show the following facts. The operators L, lambda, F, and the real Laplacian generates the even part of a Lie superalgebra. The order parts, partial and partial bar star, span a spinor representation S. Why is this span a spinor representation? This is actually given by the Kähler identity. And we also have the dual representation S star generated by partial bar and partial star. This is just you take the complex conjugate of the two operators. And the pairing is given by the following relation. So all the operators forms n equals to 2 supersymmetrical algebra. So this is a description of scalar geometry on X. And then we have the Hodge theorem that X omega be a compact scalar manifold. Then there is an orthogonal decomposition. So for the space of PQ form of X can be decomposed or also can be decomposed into 3 orthogonal spaces. So HPQ represents the space of harmonic forms. And we have the imaginary part of D bar and also the image part of D bar and also the image part of D bar star operators. So furthermore, we have the isomorphism, says the space of harmonic PQ forms is isomorphic to the D bar complex D bar the cohomology of D bar complex. So this is a Hodge theorem. And we have the following facts. The decomposition HK of XC equals to the direct sum of the following space. So this decomposition does not depend on the chosen Kähler structure. It depends on the complex structure. We also have the complex conjugate relations. And the serial duality, HPQ with H n minus Q, n minus P, serial duality. We also have the Hard-Lefschitz theorem, so which means the decomposition of Pritim cohomology. And with all the structures here, we can get a so-called Hodge structures on X. So this means Hodge structure consists of the Hodge filtration given by this decomposition, plus a pairing called Hodge-Riemann bilinear relations. And then, because this is these facts hold for only one Kähler manifold X, right? And then we deform the complex structure of X. We get a family of the Hodge structures. So this is called the variation of Hodge structures. And so on the deformation space, we have the Hodge bundle structure. So the Hodge bundle structure is also a local system with the Z coefficients. So that means it provides a flat connection called the Gauss-Manin connection, and then you can consider the solution of this Gauss-Manin connections, and you study the periodic matrix and the periodic mappings. So this was actually the center of complex geometry in 60s and 70s of last century. And then let's consider the mirror symmetry beyond the Calabi Yau manifolds. So we have several reasons to consider the mirror symmetry contained not only Calabi Yau manifold, but other geometrical objects. So the first reason is because there exists the so-called rigid Calabi Yau manifolds, which has such Hodge numbers equals to 0. That means there's no non-trivial complex deformation of this Calabi Yau manifold because this dimension is 0. Even X is compact. If the mirror symmetry holds for X and the mirror pair, that means the H11 Hodge numbers of the mirror, compact mirror Kähler manifold should be 0. But this is impossible because for a compact Kähler manifold, the H11 is not 0. So this is the first reason. That means if there exists a mirror symmetry between for rigid Calabi Yau manifold, then the corresponding mirror object should not be Calabi Yau. The second example, we can consider the final manifold. Final manifold means the anti-canonical bundle is positive. For example, Pn is a famous example. So by Holomorphic construction, Pn is mirrored to a LG model. So this LG model consists of an algebraic torus C star n with a Laurent polynomial Z1 plus dot to Zn plus 1 over Z1 times Zn. So this is a famous example to show the mirror symmetry between Pn and the LG model. The third example comes from the study of non-abelian examples. We can consider the Grossmanian manifolds, GRKN. So its mirror is also an LG model, GRn minus k of n. So this Grossmanian represents the space of k planes in Cn space. So its mirror is to this LG model, but you should take away some divisors such that this manifold is an open manifold, and then you have corresponding Laurent polynomial W defined on these open manifolds. The Laurent polynomial is defined by the pre coordinates. So here I don't want to write down the explicit expression of W. And the last one is because of Sabat's construction of Frobenius manifold for non-degenerate and convenient Laurent polynomial defined on algebraic torus. So for this model, you need also consider the LG model. And now we can understand the global mirror symmetry picture. The global mirror symmetry picture is this diagram. So in the upline, you have the Calabi Yau models. So Calabi Yau A model mirrored to the Calabi Yau B model. So in the downstairs horizontal line, you have the correspondence of LG A model to the LG B model. So from up to downward, you have the so-called CY-LG correspondence conjecture. So some node theories for Calabi Yau model, as I mentioned just now, for Calabi Yau A model, we have the so-called Gromov-Witten theory. So this is for closed string. And we also have the Fukaya category. Of course, this is the open version, but only for genus 0. And we consider the Calabi Yau B model case. We consider the variation of Hodge structure. So in this side, we can get the TT star geometrical structure, which contains the genus 0 information. But the rigorous mathematical theory has not been built for this Calabi Yau B model in terms of the deformation theory of complex structures. So in the open version side, we have the so-called category of coherent shifts. And also we have the Donaldson-Thomas invariance definition. So all the theories appeared in the Calabi Yau models. So there are many important works due to many famous mathematicians working in this field. And now we consider the conjectures related to Landau-Ginzburg model. So what's the mathematics theory of LG models? So that should be the LG to LG mirror symmetry phenomenon. And how is LG CY correspondence? So here I just mentioned one conjecture to LG-CY correspondence. So this conjecture was proposed by physicists Martinic, Warne, and Witten in the 19th of last century. And the conjecture says the LGA theory of the admissible pair of WG is equivalent to the corresponding Gromov-Witten theory of XW quotient G tilde. So this is all before the Gromov-Witten theory. Now we understand the LGA theory is just the FJRW theory. So here I just persuade you that the LG model is very important in the study of mirror symmetry. But of course, LG model has its own interests to be studied. So let's give a definition to the LG model. A complex LG model is a pair MF. So M is a complex manifold, and F is a holomorphic function defined on M. If M is equipped with a calorimetric G, we call it as a Calabi LG model. We can also define the so-called complete Calabi LG model if M is a complete manifold. Here, of course, M should be open manifold, because if you want F to be a non-trivial holomorphic function. So usually we add more conditions for MGF. MG is a non-compact complete Kähler manifold with bounded geometry. F satisfies some term condition to control the critical points of DF and its growth. Algebraic geometers usually study smooth algebraic variety. M is a smooth algebraic variety, so they can compactify M. They can compactify M to get a compact algebraic variety. So they require MF can be compactified to M tilde and F tilde, such that F tilde has no critical points on the boundary M infinity. Here I just mentioned one theory of Kazakov, Konsevich, and Pantiev in 2014. So they gave a 10 Topolov type theory, says there's no deformation obstruction for Calabi Yau type LG model. So the LG model they mentioned in the theorems refers to the algebraic one. That means they require the compactification, the existence of compactification of this LG model. Of course, this can remind you of the log geometry. Yeah, because you have the Calabi Yau pair. So this says potentially the LG model has very close relation with the log geometry. And then we turn to the study of the Terminus conditions for LG model. The holomorphic function F is called strongly tame if for any C greater than 0, we have this growth condition. So the nabla F norm of nabla F square minus C times norm of the second derivative of F should be go to infinity as the distance goes to infinity. So such kind of strongly tame condition was for manifold was proposed by me in my archive paper 2011, but more earlier for in CN case by two authors, I think in 1991 for in CN case. And then we also have the tameness. That means there exists a compact set K and positive number delta such that the norm of gradient of F is larger than delta outside K. So we have the very weak tame condition called cohomologically tame, which means there is no critical points at infinity. This has a definite definition due to Sabah in his paper of 2005, I think, yeah. They give an algebraic definition of the so-called cohomologically tame condition. So here, the following two examples were proved by me in my paper. So I found that for CNW is strongly tame if W is non-degenerate quasi-homogeneous polynomial. C star NF is strongly tame if F is a non-degenerate and convenient Laurent polynomial. So these two examples covers most interesting examples from mirror symmetry. But we also have the counterexample that polynomial does not satisfy all the tame conditions. For example, we can consider f of xy equals to x squared times y plus x, and then you take the partial derivatives of f. So you get fx equals to 2 times xy minus 1, and f2y equals to x squared, right? You see there's no interior critical points inside C2. But if you let x goes to 0 and you take y equals to 1 over x, you will 1 over 2x, you will find the possible critical points appear as infinity. So this is a counterexample which doesn't satisfy the tame conditions. Now let's consider the A model from the LG geometry. So the A model refers to a nonlinear equation called Witten equation, which is defined on the line boundaries of Riemann surfaces. So let W be a non-degenerate quasi-polynomials with a form. So W is a sum of some monomials Wi. And the Wi is a monomial, is times of those variables. And consider sigma to be a Riemann surface with k market points pi. So that is a log canonic bundle k log, defined in the following identity. So log canonic bundle is just the canonic bundle k sigma tensors with point line bundles, k point line bundles. And we have the definition of W structure. This consists of n line bundles Li on the genus G sigma satisfied isomorphism, because you can take a monomials Wj, right? You take a monomials Wj, and then you insert the line bundles into the place of the variables, and then you get the tensor products of line bundles. So this line bundle should be isomorphic to the log canonic bundle. So if the n line bundles satisfy this condition and they exist, and then sigma together with this line bundle is called the W structures. So here are the examples. So the first example, you can consider the a to r-1 polynomial. Here, because this polynomial has one variable, so there is only one line bundles on sigma. This line bundle, the rth power of this line bundle should be isomorphic to the log canonic bundle. So the second example is dr polynomial, because it has two variables, and then you should have two line bundles, L1 and L2. And because dr polynomial has two monomials, so the first monomials is x to the power of r-1. So this requires L1, the r-1 tens power of L1 should be isomorphic to k log. and L1 times with L2 square should be isomorphic also to the log canonic bundle. So this is the W structure over for the DR. And the third example is E7 case. So similarly, we have those isomorphisms. So using the W structures, we can define the matrices on each line bundles, because we can choose the calamatrical H on the Riemann surface sigma. So this is equivalent to choose a matrical on the log canonic bundle. And because of the W structures, you can fix the matricals on the line bundles. So by the W structures. So with those geometric settings, we have the following definition of Witten equation. So Witten equation is the equation for the unknown sections U1 to UN. So each UI is a section of the line bundle Li. They should satisfy the following nonlinear Cauchy-Riemann equation, Cauchy-Riemann systems. So d bar UI plus this nonlinear term should be equals to 0. So I here is defined by the metric which gives isomorphism to some line bundles. So you see to make this plus meaningful, we should let this term d bar UI and the second term they lie on the same bundles. So this can be done by the W structures. So this makes the definition perfectly. This is the definition of Witten equation. So the aim of Witten is construct the virtual cycle on the modular space of W curves and generalize his Witten conjecture, because the Witten conjecture says the intersection numbers of precise class defined on the modular space of curves should be related to the KDV hierarchy. And if one consider the more general case, for example, ADE case, and then we get a more generalized modular space consisting of the W structures, and then the intersection numbers of this modular space should be equivalent, should be related to some other integral hierarchies. And he conjectured that should be related to the so-called Grunfeld-Sokolov hierarchies. So here, there are difficulties to treat this Witten equation. So one difficulty is because if you want to consider a degenerate theory, that means you must consider the degeneracy of line bundles. This led to the discussion of orbifold line bundles, orbifold surface, and orbifold the other things, and there are some other very difficult problems. So let's take a look at the simple equation. The first example, the R-spin equation. So R-spin equations is on the Riemann surface, you have only one line bundle, right? And then you have only one section. This section U should satisfy this nonlinear equation. This is called the R-spin equation. But U is a complex function. And then we can take a look at the DR equations. Because DR equations has two variables. So this is a system, this is a Cauchy-Riemann systems. I don't want to explain the details about the equations. I just let you have an impression of this equation. So you see this is a system of two unknown sections, U1 and U2. And they satisfy these equations near on the Riemann surface, on the Riemann surfaces. But for different marked points, this equation has different expression. Here we have three forms of the equations defined on the different marked points. And then the main task is to solve these equations. This turns out to be a very difficult task, but by a series of papers, we have proved, we have successfully, in some sense, solved this equation and proved this theorem. So this work was done from 2002 to 2009. So given a non-degenerate quasi-homogeneous polynomial W and admissible group capital G, we can build a cohomological field theory, and now it's known as the Van-Jarvis-Witten theory. So this theory is a parallel theory to the Gromov-Witten theory in the study of mirror symmetry. So the whole construction is very difficult. So that means we have to understand, we have to understand the nonlinear Cauchy-Riemann equations. For example, we need to study the index theory and the asymptotic behavior of the solutions near the marked points and so on. So anyway, it's very difficult to have such a theory. So actually, the paper appeared in Annals of Mathematics is 100 pages long. And so recently, we are approaching to finish a monograph up to 400 pages to build a very rigorous foundation for the invariance. So as the application, Application 1, we can prove Witten's and ADE singularity mirror symmetry conjecture in 4 journals. This is a fast example for LG to LG mirror symmetry. The application 2 is we can solve the generalized Witten conjecture for DE cases. So just to remind you, is the A1 case is called the Witten-Kontsevich theorem. And the AR case for R greater than 1, this was partially resolved by Witten and YP Lee for the lower genus case, and for all genus by Faber, Shadring, and Zwankinen. But we built the rigorous foundation for the Aspin curves. And recently, we have other algebraic construction method due to Polishuk-Weintraub using the matrix factorization, and also Zhang, Li Jun, and Li Weiping, and also Chang, King, and Li. Those are the algebraic construction. So this opens the further research of LG models. So people published a lot of papers on the LG to LG mirrors, LG to CY correspondence, gauge linear signal models, and so on.
Huijun, sorry, can I ask you one question?
Yes.
So for your theorem 0.9, have you proved it only for non-degenerate quasi-homogeneous polynomials, or also for polynomials satisfying the same conditions you explained before?
Actually, so here we need this quasi-homogeneous to be non-degenerate in the A theory. So that means it's strongly tame.
Yeah, I know you've explained that, but maybe it is true also for general.
But for the A theory, because it comes from the n equals to 2 supersymmetrical Landau-Ginzburg model. So the supersymmetry requires this polynomial to be quasi-homogeneous.
Okay.
Yeah, this is a condition automatically from the study of the supersymmetry. So that means it can. This A theory can only be built for the quasi-homogeneous, for the polynomial having the symmetry.
Okay.
Yeah, we don't know how to define. Even we don't know how to define the Witten equations.
Mm-hmm. Thank you.
Okay, so let's turn to the other stories, the B model. This is also quite an interesting story because it leads to the study of Schrodinger equation and its deformation. Let MF be a Kählerin LG model. There are the twisted operators. As usual, we have the, because this is Kählerin, that means M admits a Kähler form. So the Kähler form gives the definition of Lefschetz operators L, lambda, and F. So the three operators forms SL2C algebra. And we also have the D bar F operator. Sorry, here I have not written down the explicit form. Actually, D bar F equals to D bar plus partial F Verge. Yeah, so it's just such operates. And we have DF, and also the dual operators, D bar F star and DF star, DF star. We have the twisted Laplacians, delta F. So we have the very similar conclusions compared to the compact Kähler manifolds. That means the operators L, lambda F, and delta F generates the even part of a Lie superalgebra. The odd operators partial F star spans a spinor representation S due to a Kähler identity. We also have the dual representation S star generated by partial F and partial F star. And the pairing is given by the following relations. So all the operators form n equals to 2, the supersymmetric algebra. But there is one very unusual thing, is the following specialty, because I found this equality. You can define the Hodge star operators as usual, but when you consider the commutativity of star and delta F, you will find star composite with delta F equals to delta of minus F with star. So this phenomenon is different to what happened on the Kähler manifold. It turns out to be very important to prove the vanishing of zeta function later. So let's take a more close observation to this twisted Laplacian. So if we take the local coordinates, delta F has the following expression. So you can see this is the usual D bar operates plus a middle term. This middle term is relates to the second derivative of F, and then plus the norm of delta F square. So when acting on 0 or the top forms, this operator has the following form. So this acts as a scalar operator. So you can see delta F is just delta plus this potential form. This is just the Schrodinger operator. But if you consider the operation on the forms, this operator can be considered as a matrix Schrodinger operators. So we can consider the one-dimensional LG model. So here, if we consider the Euclidean metric on C with a holomorphic function F, so we have such Schrodinger operators. In particular, if F equals to Z squared over 2, delta F is a complex one-dimensional harmonic oscillator. So this complex one-dimensional harmonic oscillator consisting of a combination of two real one-dimensional harmonic oscillators. And then I proved the following theorem in my paper, archive paper 2011. So many of this paper is very long, but not published. But many of the results published in the as appendix in the other papers. So the main theorem is as follows: suppose that MG is a Kähler manifold with bounded geometry. If MGF is a strongly tame LG model, then delta F has purely discrete spectrum, and all the eigenforms form a complete basis of the Hilbert space L2 of those forms. So as there is an important corollary, says the LG models Cn with this non-degenerate quasi-homogeneous polynomial, and also the Laurent polynomial F defined on the algebraic torus with this metric are strongly tame. You only need to check the strongly tame condition and then see the two models, they satisfy this analytical condition. So this means the corresponding form Laplacian has purely discrete spectrum. This is an important corollary. So once we prove this spectrum theorem, we can get the Hodge decomposition for twisted operators. That means the L2 space of K forms can be decomposed into three spaces. So HK is the space of harmonic forms, and then the image of D bar F plus image of D bar F star. And we can also prove the only non-trivial harmonic form space is just H2n. And Hn is isomorphic to this space, omega n modulo df verge omega n minus 1. And this results, this Hodge-Derives theorem recovers the partial information of the local algebra of the singularity F. That means we can use the analytical way to study the singularity theorem. And then we can go further in this paper. We can construct the TT star structure on the Hodge bundle over the deformation parameter space. And for some singularities, we can get the Frobenius manifold structure. So the TT star structure consisting of the genus 0 information. And also very interesting thing is we have the Gauss-Manin connection. That means it can provide various integral system. It's also related to the Riemann-Hilbert problem, Panlev equations. The advantage of this story is you take an LG model, you just you need only to check the strong tame condition. Then all the conclusions hold automatically. And for this Gauss-Manin connection, you can also solve the fundamental matrix of this equation, which can be written as a periodic integration or equivalently some oscillating integral. So recently, with my two students, we can also prove the following theorem, the so-called LG to CY correspondence. So there is a bound isomorphism from this ELG TT star structure to E bar TT structure on the CY part. And this phi tilde is given by the big residual map constructed by Steenbrink. So these are LG-CY correspondence. So the meaning of this theorems means we can study the topological or geometrical information of Calabi Yau hypersurface in terms of the LG model. But we know for LG model, we can not only perturb it in a marginal way, but we can also perturb it in a relevant way. So that means the non-conformal information can decide the conformal information. But for the B model, the genus 1 case is also very important. Its conjecture is related to the discussion of torsion invariance. So with Fan Hao, we also can prove the following theorem. This result published in Huijun GMS. We have proved the following index theorem. So if F is a strongly tame quasi-homogeneous polynomial satisfying some conditions, some technical conditions, the Milnor number mu F is given by the Gaussian type integral. So mu F can be expressed in this way. And particularly, if we take Fz equals to z squared over 2, then we obtain the well-known formula. So now you can, you know, this formula has a different meaning. It can be deduced from the singularity, from the LG model, from the singularity theory. And then we can study the heat kernel of this twisted Laplacian, define the ith zeta function, theta Fis. So I here means the number operators we can take I times. So it's expressed in these factors. So in this way, we can define the zeta function. This zeta function is analytical in the domain with the real part of S greater than 2n. And TF2, this, so this is a portion, so let's forget it fastly. And we have the following theorem. Let F be a non-degenerate quasi-homogeneous polynomial, then the fast zeta function equals to vanishes. This is very important because one can consider the so-called ring-single holomorphic torsion on a compact Calabi manifold. It turns out the zeta function for the compact Calabi manifold also vanishes. So here we have the correspondence. We can prove the fast zeta function also vanishes. So the proof depends on the commutativity of a star operator on the twisted Laplacian operator. And to define the ith torsion type invariance, we need to extend the ith zeta function, theta Fis for I equals greater than 2. Usually we take I equals to 2. So we need to extend this ith zeta function holomorphically to C. This requires a symptotic formula for heat kernel. So due to a technical reason, we assume that F is a homogeneous polynomial. Then by the trace class result and the asymptotic formula for heat kernel, we can define the ith torsion type invariance because we can renormalize, because we want to extend the zeta function analytically to the whole space C. And we use asymptotic behavior to renormalize the zeta function, such that the renormalized zeta function is analytical at the region. And then we define the torsion type invariance in this way as usual. So it turns out for I equals to 2, T2F is analogous of the BCOA torsion appearing in the physical literature for the Calabi Yau hypersurface. So we have the correspondence. So let's see some examples. If we take F to be the very simple Morse function, z squared over 2, then the zeta function is as follows. It's just the transition of the Riemann zeta function, and the torsion invariance is given by this number. So besides that, one can consider the LG model on the algebra torus C star. with this Laurent polynomial. So this Laurent polynomial in mirror symmetry corresponds to the geometry of Riemann sphere. And my student Tan Xinxin, in her thesis, can prove delta F is a trace operator, and that is a expansion, heat canal expansion. So this expansion is very interesting because delta F is a Schrodinger operator. It's very rare to have the results of heat canal of Schrodinger operators. But for this example, he can get this formula. So here you see the log T appearing in the expansion of this heat canal. So besides this heat canal expansion, she can also prove the varnishing of C1 Ft for the deformation of F and get the DD bar formula for torsion, for this torsion.
Sorry, just can you explain what are the coefficients CK and DL? Yeah.
CKDL, yeah, CKDL are some constants.
I mean, both summation signs seem to be similar up to the renaming of the coefficients. So
sorry, here maybe the bracket is here.
Yeah, okay.
Yeah. Sorry, yeah. And he can also get the DD bar formula for torsion, T squared. So DD bar, so you can consider the deformation of F, and you have Ft. And for this Ft, you have the torsion, right? So this is a function defined on the deformation space. And then you take the DD bar derivatives, which was proved to be equal to some Yukawa couplings. And then Dai Xianze and Yan Junrong in 2020, they removed the technical problems in our papers. Then can generalize the results to more generalized case, including any non-degenerate quasi-homogeneous polynomials. So this is the story for the genus one case. So it's conjectured the torsion invariance defined here should be related to the genus one potential function from Gromov-Witten theory, and also relate to the BCOV torsion appearing in the Calabi Yau hypothesis. So finally, I give some problems related to the LG model. So in the FJRW theory, we need to assume W to be non-degenerate. So what's the situation if W is just a general quasi-homogeneous? So what's the analytical properties of the solution of this equation? This has not been done before, but this system is very interesting because it's a nonlinear Cauchy-Riemann equation defined on the Riemann surface. It's absolutely deserves the further research from the point of view of analysis. So the second question is also very important. The problem is if F is homologically tame, so what is the spectrum? What is the spectrum behavior of delta F? Is zero is a discrete spectrum of delta F? This is very interesting, yeah, because it has a potential application to the study of topological insolate in physics, and also because on the universal deformation space of singularities, Saito can construct his forbearance manifolds, while the algebraic methods. The problem is how to reconstruct Saito's forbearance manifold structure, while boundary value problems. We have made some progress with my students. We consider some Debye-Neumann problem with a domain to be pseudo-convex. And also there's some other questions related to the open version. The so-called Mori-Gadan element conjecture by Gaito, Mura-Witten, arising from Weber algebra, the so-called infrared algebra. And then this algebra reformulated by Kaplanov, Kontsevich, Soyberman in terms of second Politov structure. Of course, the relate to this conjecture, the first step is to construct the Fukaya category of LG model for holomorphic Morse function. So this step actually was finished by me and two of my cooperators in 2018. It appeared in the archives. So finally, I want to mention the study of gauged linear sigma model. So this is a very big model containing the LG and the CY models. So the first quantum invariance was constructed by me, Jarvis, and Ron in 2018 in geometry and topology. In the case of geometrical phase, so our construction is purely algebraic in algebraic way, and then later the related gauged Witten equation was studied by Gang Tian and Guangbo Xu, and also the other works from the viewpoints of categories theory. And I think I stop here. Thank you very much for your attention.
Yeah, thank you for your talk. Maybe someone have questions.
Yeah, is it possible to speak, to ask questions?
Sure, we hear you.
Yeah.
Yes.
So first of all, I want to thank you for this profound lecture with numerous relations to many mathematical problems. I have some general question. We can consider mirror symmetry as a symmetry between symplectic and complex geometry, just roughly speaking. Do you know if there exists some extension to the supermanifolds of this mirror symmetry? I wonder if there is some generalization.
Which manifolds?
Supermanifolds.
Supermanifolds.
Yes,
No.
some supersymmetric generalization. If it exists, I don't know.
No, I don't know. I don't know any examples or papers from the point of view of supersymmetrical objects.
Yeah,
But
because
maybe,
for example, for sigma model, there is a supersymmetric generalization of sigma model and things like that.
maybe I can mention the geometrical Langlands program because geometrical Langlands program means you can start from n equals to 4 super Yang-Mills theorem, and then after twisting, you can reduce this story to two Huijun modular space. So one Huijun modular space is given by a Lie group, and another one is by the Langlands dual Lie group.
I see.
So the problem is there is a mirror symmetry between the two modular space. You can consider the nonlinear sigma models to the modular space of Huijun equations. Yeah. So that means you can consider either Gromov-Witten theory on the modular space of Huijun equations, or consider the Fukaya category. That's what I know.
Yes,
And actually the duality comes from the S duality.
I see. Thank you very much.
Okay, you're welcome.
Sorry, may I ask a stupid question, maybe?
Please. Yeah.
Just you're speaking about the torsion in the last part of your lecture.
Yes.
And you also mentioned that this torsion is a generalization of Ray-Singer torsion. Well, as much as I remember about Ray-Singer torsion, one of the most important properties of this torsion is its relation with Reidemeister torsion, which is purely topological and purely combinatoric. So I just wonder whether there is a combinatoric side of the story related to the torsion which you constructed.
So firstly, I have to say I don't know, because this torsion invariance can be potentially used to describe the singularity, right?
Yeah.
And I think this is a new story since the research of singularity theory. So the first point. So the second point is we can consider the BCOA torsion defined on the Calabi Yau hypersurface. This was built by the physicists. They get the torsion, the so-called BCOA torsion. And according to the LG-CY correspondence, we have the definition of such torsion from the side of LG model. And the problem is, do they have some relations? This is genus 1 LG-CY correspondence.
I see.
So far, yeah, it was unknown. Maybe it's related to one need to consider some localization technical.
I see. Thanks.
Okay. Thank you for your talk again.
Sorry, can I ask a question?
Yeah, sure.
Okay, yeah.
In your definition about the Riemann-Hilbert problems, the conditions that you find is for the some superpotential on the of Morse or Morse function? Or can you explain more about the Riemann-Hilbert problem that you find, or you in?
Yes. Yes. So maybe you remember we considered the only one holomorphic function f, right?
Yes.
But actually you can times C star parameter called T. So and then you can consider TF, right? But this is in some sense at first glance similar to the so-called Witten deformation, right? You put a parameter T in front of F, but here the T is taken to be a number in C star, and then you run all the story. You get a Gauss-Manin connection, not only defined on the parameter space, but defined on the parameter space times C star, and the integrability condition appearing in the branch of C star should be related to the Riemann-Hilbert problem. So this point was explained in my 2011 papers. You can find from the archive.
Okay.
Yeah.
Thanks.
Okay. Thank you again. If
Okay,
there
thank you
are
very
no
much.
more questions, then we will finish our seminar for today.